Let's all welcome David Myers, who's going to talk again about open dynamical systems, so this time about hierarchical planning.
Thanks, Paulo. So I was here a couple weeks ago, and I talked about a general definition of open dynamical system, and I'm going to build off that, because in that talk I told you what a generalized open dynamical system was, but I didn't tell you a notion of morphism between that and between them. And that's kind of a bad place to be if you're a category theorist. So this talk is all about morphisms between open dynamical systems. So I'm going to start by going over what the definition of an open dynamical system was, although I'm not going to motivate it as much as I did in the last talk. It's going to be a bit more austere this time. But then hopefully we'll have some nice motivation when we come to these notions of morphisms. So in particular, we're going to see that trajectories are a kind of morphism between open dynamical systems. And then also hierarchical planning between various automata. So when you have various machines running at different scales, say taking instructions and executing them, and you want to be able to plan at multiple different scales, we'll see that as an instance of a morphism of open dynamical systems. So a dynamical system consists of a notion of how things may be, which we call the state, and how they will change given how they are. And so we're going to start our axiomatization of this general idea with a notion of bundle. So the way that things might change might depend on how they are. So this is our idea, the way things can change depends on how they are. So we're going to axiomatize that as a sort of bundle. And we'll think of this as the bundle of changes sitting over the bundle, the space of states. So this is a heuristic. What this would say is that for any state, we have a space of changes that are possible in that state. Maybe not determined by the law of our dynamical system, but which are possible. So this will be formalized formally. This is what we call a indexed category. And that is a contravariant functor bun from some category C of spaces to the category of categories. So this is the category here of spaces. And the contravariance there says that to every function of spaces, we're going to get a pullback of bundles going back along that. So as an example of this, we have, e.g. index categories. We can take the slice indexing, the self-indexing of any category with pullbacks. So in particular of set, we have bun equal set sliced over some object going from set op to cat. We can also do things where the bundle is kind of trivial. In other words, how things can change is not going to specifically depend on the state. It will depend on the state. The particular dynamics will depend on the state, but the range of possible choices won't. And so that is a nice example here. Bun can be the Co-Kleisli category of this thing cross from set op to cat. And what this means is for every set, we get a comonad, which is that set cross another set. And that's a comonad structure given by the comonoid structure on every set given by duplication and deletion. And So that gives us a functor from set op to cat, sending every set to the co-Kleisli category of this comonad. And we can think of this as functions that exist in the context of that set. So if we have a context here, we can think of this as going to the category co-Kleisli of C cross dash. And this is the category whose objects are sets and whose maps are functions from C cross X into Y. So those are functions contextualized by C. Oh, that's nice. We can also have bundles be something that's more familiar as the notion of bundle. We could have bundles be submersions from manifolds to, and this sends every manifold to the category of submersions. And the reason to take a submersion is that pullbacks along submersions exist in this category. So it's in a way, it's sort of like very much like a special case of this, but we can only use submersions because otherwise we couldn't take those pullbacks. So these are our various notions of bundle. Also, I might say that another important one is the bi-Kleisli category of the similar product comonad and any commutative monad for M a commutative monad and this is functions in the context of C that have effects coming from the monad M. So in particular, this is nice if we want probabilistic dynamical systems or non-deterministic dynamical systems, and so on. Okay, so given such a thing, given such an index category, so given bun from C op the cat, we define the category of bundles is going to be the Grothendieck deconstruction, so I'm going to call this bun underlined, and it's going to be the Grothendieck deconstruction of this functor. So explicitly, what this means is the category of bundles has objects, pairs of a base space and a bundle sitting over it. So that's B is a space in C, and E is a bundle over B. And its morphisms are going to be bundle maps. And what that means here in this abstract setting, and this effectively is just a fixed notation, is there going to be pairs of maps like this, and I'll write a bundle map with two arrows pointing this direction, so you remember that they're pairs. And that will expand as f is going to be a function on the bases, and f lower sharp is going to be a function from on the total spaces, or on the fibers really, in the bundle, into the pullback of the second one. So it's covariant. So if I was using these sort of bundles where they're maps like this, then this would be a square. So in here, this category is just the arrow category of set. In here, it's going to be a, well, I guess it's not a immediate to describe what this is in terms of other things, but it's going to be a category where you have the base is, you have just pairs of sets, and your maps are going to be pairs where one of them is contextualized by the base. So contextualized maps where the context varies. In this one, it's going to be submersions, just like this. It's going to be two submersions, and a map like that's going to be a square. And in this one, it's going to be something even more interesting. It's going to be maps contextualized by this base, and also having effects from this monad, so mapping into this monad. Okay, so that's the definition of the category of bundles. Now we'll come to the category of lenses. So the of lenses. Oh, and for the rest of the talk, I'm going to effectively fix this index category of bundles. So a lens in this notation comes from computer science, and this is in particular using the idea of generalized lenses, which is due to Spivak, is going to be here. So the category of lenses is going to be the Grothendieck deconstruction of the opposite of the category of bundles. So what that's going to mean is that the objects are the same as the category of bundles. The object is just a bundle sitting over some base. But now the morphisms are going to be something different. A morphism here is going to be a pair, and to fix notation, this time we're going to write the arrow on top going backwards to remember that contravariance, which is up here. And this will be a pair of a map on the base and this map F upper sharp, which is going to go from the pullback of the bundle that's over B prime to the bundle over B. So it's exactly contravariant version of this. Now, if you take that notion of lens and you apply it to this Koch-Kleisley category of bundles, or Koch-Kleisley index category of bundles, which is in here, you will find that this is exactly what is normally called a lens, or a bidirectional lens in, say, the Haskell literature. And that's where the name comes from. And I'll mention that unlike most categories, we name the category of lenses after its morphisms, not after its objects. Its objects are exactly the same as the category of bundles. They're bundles. Okay, so why did I do that? Well, it's because this is the setting that we're going to work in order to define our dynamical systems. I'm sort of running here. I need one more tool, which is, finally, I need to define this bundle of changes. So what is that? So the bundle of changes. So we assume we have a section of the category of bundles, which we'll call T. You can think of T as standing for tangent. What this is going to do is send a space, C, to a bundle, TC, in bun C. And we're going to think of this as the bundle of possible changes you can make in a given point here. So, in particular, we might have here, leave myself enough space, here we might want T to be the tangent bundle. Here, we're going to want T of C to just be C cross C projecting down to C. In other words, here we'll say that the possible change you can make in a certain state is to go to any other state. You're unconstrained. In Koch-Kleisley, we'll take TC equals C. In other words, the same thing, except now we don't have to put it as a bundle. So if you're in any state, you can transition to any state. And similarly down here, we'll take TC equals C. This is functorial, but I won't go into that in a second. I guess what I'll say is this goes to TC here. And if I have any map here, F to C prime, then I'm going to get a map TC to F star of TC prime. So it's a covariant one. And this is going to be called TF. And so in the case of the tangent bundle, this is just the push forward of vectors. The differential. Okay, So now we're finally ready to define an open dynamical system. So, F. An open dynamical system is a lens of this form. Great. I'm glad that's clear. Let's go through it. So there are 3 pieces of data in terms of objects, and then there's 2 pieces of data in terms of morphisms. So we have a space of states, S, a space of outputs, or orientations, O, a bundle of acceptable inputs, which is a bundle over the orientations saying that I'm able to accept this input given this orientation, given this output. So for example, when I'm looking to all of you, I get to see your beautiful faces. When I look to the board, I get to see a bunch of chalk. So the inputs I have are different depending on my orientation in space. So this is also that my orientation in space determines what I put out. So you're able to hear me. I'm talking when I face to you. The more I start talking to the board, the harder it is for you to hear me. Yes?
Is that bun of I or bun of O?
Yes, sorry, it's bun of O. Thank you.
So T is some I don't understand whether T is as a parameter of this, or if T is some standard fixed once and for all.
Yes. So we're going to fix the index category and a section of its Grothendieck construction.
Okay.
And that's a part of our setting in which we can define. So maybe I'll say for bun, comma T as our setting. Okay, and then we're going to have this lens. So the lens breaks into 2 parts. It consists of a readout function and that is R, and it goes from states to outputs or orientations, and it says I'm going to output this in this state. And then we also have an update function. And this goes from R star I to TS. So what does that say? It says the update is going to take an input. But remember, this is happening in the bundle. So it's going to take an input that's valid for a given state. And then it's going to give you a change that's valid in that same state. So, in particular, we can see a few examples of these. So, e.g., so for the Coke-Kleisli one here, let's say, maybe I can number these. 1, 2, 3, 4. So for the Coke-Kleisli one, which is 2, but it's the simplest, a Coke-Kleisli dash, cross dash, comma, C maps to C. This is all the data. Open dynamical system. Is a deterministic automaton. It has a set of states S. Remember, TS is the same thing as S in this example. Here. It has a set of outputs O, and it has a set of inputs I. It has a function which takes every state to an output. This is its readout. And it has an update. And this is taking place in the Coe-Kleisli category of S cross. So this is actually, in this case, a function from S cross I into S, because TS is S. And so that is, it takes a state, it takes an input, and it gives you a new state. So this is a deterministic automaton with output alphabet O and input alphabet I. Example 1 is the same.
This is I of O.
I of O?
Yeah, I can depend on O.
In this case specifically, it does not, because the Coe-Kleisli categories all have the same objects, which is just their objects are sets. It's only their functions that are different. But for one example here, which is the slice construction on set, now I really does depend on O. And so this is the same, but the input alphabet, in a given state depends on the output of that state. This is useful if you wanted to find cascades for these kinds of things. I won't talk about that at all. For 3, so for 4, I'll say this is also the case, but you add in the words non-deterministic automaton, probabilistic automaton. So 4, ditto, plus non-deterministic. So that's when M is equal to power set. Or probabilistic. That's when M is equal to the distribution monad or finite Giri monad. Or you could have linear. And that's when M is K vector space monad, etc. You pick your monad, and you'll get that flavor of automaton. Okay, that leaves the more important example of, oh no, how do I do this? If I put that there, it's gone. But if I put this here, I want to keep this up a long time. I'm going to take off this half. So that leaves one more example, which is 3. And this is a particularly nice example, because this is the continuous time dynamical system. So this is something that maybe will look more familiar. I want to do a specific example of this. So first, in the abstract, what this is going to do is we're going to have, I'll read it here. We're setting ourselves up here in manifolds, so everything inside is going to be a manifold, every function is going to be smooth, and then a bundle is going to be a submersion over that. So in other words, we have a manifold of states, S, we have a manifold of outputs, O, we have a submersion over O, which it gives us our bundle of inputs valid in any given output, and then we have a smooth function, which sends every state to its output, and then we have an update function, and this is interesting. It takes any input it has, and it gives us, that's valid in a given state, and it gives us a tangent vector at that state. So I would like to show how this is going to be, how you can do this in an example. So let S be foxes times rabbits, and we'll consider these both to be R. So this is going to be R cross R. And we'll let O equal S and R equal id. This is just a trick I'm going to use a lot in this talk to simplify things. So there's actually a factorization system on lenses that allows you to always factor something of this sort. Okay, and then we're going to let I be S times R4 projecting down to S. Okay, so this is the setup data. Now I'm going to give you a function, an update function. I've given you the readout, and here's my update. It has to go from R star I, but R is the identity, so it just goes from I to the tangent space of S, and it's doing it over S. So this is S cross R4 over S. So what does it mean to be over S? It means the thing I paired up S here has to go to a tangent vector here over S. So what's it going to do? We're going to say U of, it's going to take a thing in S, which is here, is a fox and a rabbit. And it's going to take these 4 variables here, which I'm going to call A, B, C, D. And it's going to have to give me a vector. And that vector will be this. I'm going to take AR, I'm going to subtract off BRF, I'm going to multiply that by DDR, and I'm going to add to that DRF minus CF times DF, DDF. So you can see this is a tangent vector. It's going to be a tangent vector over the correct point, just because these here are the ones sitting there. And so at this point, does this look familiar? Anyone? Yeah, so this is the Locke-Volterra predator-prey model. It may look a little bit different than what you expected because usually it's presented in the form of a differential equation. And here I've presented it in the form of a vector field. So how do we square that? How do we go between those two notions? Well, the answer is that a solution to this system, a trajectory in this state space, will be a function which satisfies the correct differential equation. So that brings us, finally, halfway through the talk, to trajectories.
So I'm
Yes.
sorry, can I just take a beat?
Please.
This d over dr is a, what is that?
So our manifold is S. It's R cross R, and I'm going to say it's coordinatized by the two variables F and R.
Yeah.
And so its tangent space is spanned by the two coordinate differentials df and dr, and those are these things.
Okay.
So those are tangent vectors.
Okay, so that explains what dr is. I'm not sure it explains what d over dr is.
D over dr is the tangent vector in direction r.
If vectors act on covectors by acting on the germs of the functions that, well, this is one of many ways you can construct things. You can think of d over dr as acting on germs of functions just like a vector would. Then you can actually identify these with vectors.
There's no issue for there's no change in the direction of R.
Okay, I mean, sure, but I mean, yeah.
This is
I also
just
kind of
like
like
R with an arrow on
real
top.
definitions, right? Instead of just the.
It is
Something in the middle of the real definition and the intuition.
the tangent bundle can be defined as the derivations on the space of functions, right? And these are two derivations on the space of functions,
Okay.
so they're vectors.
Okay.
And it's a vector space, so I can add and multiply them by scalars,
Okay.
and at every point those are scalars.
Okay.
Okay, so I'm going to talk about trajectories now. So a trajectory will be our first kind of morphism. Trajectory is going to be a covariant morphism. So definition, can people see it when it's in the shadow under here? Okay. Covariant morphism from UR, and covariant morphisms I will write in this way with two arrows pointing to the right. And it's going to be a map on states oh, I'm going to write the domain without a prime and the codomain with a prime, and everything will have the same notation as up there. So we have a state function, and then we're going to have a bundle morphism between the interfaces. So I call these input-output pairs, input-output bundles, the interfaces, and it's going to be a bundle morphism, a covariant morphism, like this, such that the obvious square commutes. Now in this case, there's no obvious square, but I'm going to write one anyway. So here's the obvious square. We have S and TS, and then we have this lens thing here, which is given by UR. And then we have this bundle map, which is given by phi and T phi to S prime, TS prime. And here we have another lens map here, given by U prime and R prime to I prime, O prime. And here we have F sharp, and F. And this is what I'm saying commutes. Now, I haven't told you how to make these two different kinds of morphism commute, to compose them. They can't be composed. Unless someone stops me right now and says, I really want to know, I won't tell you. Is that all right? Do you really want to know?
No, I don't.
Okay.
But wait, is this just like a co-slice category of T?
No. No, it's a little more complicated than that. The reason is that these are not the same kinds of morphism as this. So it's not exactly a slice. However, it is a co-slice in a certain double category. And I'll come back to that at the very end. Okay, so maybe I should write this out in an expression, but basically there are two squares, and there's only one way, if you write it down, for this to line up, given that you have to pull everything back to the right place. Those diagrams are the ones that commute. If we work out what that says in a special case, so here's so consider this this dynamical system. It's a very simple one. Its state of space is R. And its input is R. And the bundle sitting over it is the identity at R. And the only thing it does is this. So the readout of this is the identity. And so DDT here must have this form. It must go from R to TR. And this has to happen over R. So this equals R. This is there. So this is just a section. And this I'm taking to be the standard vector field on R. So this is my clock. It's my dynamical system of time where time just flows at a standard rate, which is fixed by this vector field. Okay, so if I take a covariant morphism from this into my Lotka-Volterra system, what I'll get is this. I'm going to get, so covariant dt in to UR, where this is UR from the Lotka-Volterra model, is, first of all, a trajectory. And I'll try and motivate that now. So first we're going to have a function on states. So that's going to go like this. We're going to have gamma. And gamma will go from R to S. Now S is foxes and rabbits. So I can also write this as gamma equals FR, where now FR are functions of T and not just formal variables. And then I'm also going to have an input one. This is R. It's going to go to I. And it has to have this this feature, right? So this is F sharp. I'm not going to talk about F because by the commutativity of one of these squares and the fact that this is the identity, it's going to be forced to just equal R composed with gamma. And so it's not going to be important for us. So we're just going to have the data of the top map, F sharp. And that one is going to go from, I should say this. Technically, it's going to go from gamma star, or sorry, R to gamma star I. And what does that mean? Well, that means it's going from R, and it's going to give us elements in I, which is a state. So I is going to equal S, and then 4 things, A, B, C, D. But it has to live over gamma. So that forces that S to be gamma. So in fact, I is just 4 functions, A, B, C, D, these parameters. And then we have to look at what it means for this other square to commute. So I'm going to do this heuristically. But the basic idea is this. Suppose you start in this input. You update your system. And then you push forward on the differential. That should be the same as passing forward to this new thing here and updating that system. And if you write out what that means, it's going to mean this. Well, you write it in a single thing, it's d gamma, but we're going to split it up. Gamma is fr. So I'll say the dr dt in t has to equal at of rt minus bt of rt ft, and df dt t is equal to ct rt ft minus dt ft. So this is really a solution to the logical Volterra model, except with one special feature, which is that the constants in the logical Volterra model are no longer assumed to be constant. I allowed them to be parameters that I also vary with time. Now the nice thing about this, and if you saw the previous talk, you'll have a better sense of this, is that when we have these open dynamical systems, we can wire them together. We can wire outputs of one to inputs of another. So what we could imagine is that the birth rate, A, of rabbits is affected by the proliferation of grass. They're the things they like to eat. And so the fact that this is an output means that if we had another system that was modeling the growing of certain kinds of plants that rabbits eat, and they outputted the population of those plants, we could plug that into this parameter and have that controlling this. So that's sort of the reason to have these open dynamical systems. That's the notion of a trajectory. Is there any question on that?
Yeah, wait, so this isn't a general definition, or this is very specific, kind of a bundle on tangent space. Are you saying like any covariant morphism is a trajectory?
Good question, thank you. No, I'm saying that trajectories are covariant morphisms. Other examples of covariant morphisms include quotient spaces and subspaces and stuff like that.
Well, is this some kind of like monoidal unit or something?
Paolo and I tried to figure out how to characterize this particular thing, this clock. And yeah, it's a little, yeah, we almost did it, but so far I think like it's sort of, in all these examples there's an obvious choice.
Yeah.
And we don't know how to like formally have that choice pop out of the math, yeah, so.
What would you guys like in case for like general trajectories? Would they like?
We use the natural numbers.
What?
I use the natural numbers with plus, so the ticking clock.
Oh, that makes sense.
Yeah.
Yeah, but if you use some other monoid, would you get like some Reith product of semigroups or something?
Yeah, I'm not sure about the Reith product of semigroups, but if you used another monoid, you would get trajectories of that shape. So, so for example, if you use something that said went for so many ticks and then was fixed, you'd get trajectories that end in a fixed point. Any other questions about trajectories? Okay, I'm going to move on to hierarchical planning. Okay, so the basic idea of hierarchical planning is that, let's say we're trying to tell a robot how to do something. Now, if you want to tell a robot how to do something, you want to say like, okay, hey robot, go down and get me some cookies from the break room, so because I'm hungry. And the robot will say, okay. But then the robot will think like, okay, how do I get there, right? I have to go out this door. I have to walk down the hall. I have to go into the room. I have to get the cookies, and I have to come back, right? Okay, that's one layer. But then another part of the robot has to figure out, okay, so I'm here. The door's over there. I have to get there. How do I get there? Well, I'm going to take this path. Then another part of the robot's going to say, okay, I have to take this path. I have to move my servo this way. I have to move my servo this way. I have to move my servo, you know. Then there's increasing layers of fine-grainedness in these systems. And each one of these systems can be modeled as one of these open dynamical systems. There's certain kinds of automata. Often the cases use a certain monad, which is distributions together with a action of the monoid of positive real numbers, consisting which is counted as a sort of reward for certain actions. So you have an expected reward for certain actions, and that's how you have algorithms that work on that. So you can do it with that. I'm going to do it with discrete stuff because it's going to be easier to think about. But I couldn't help myself, and I wanted to do it with a little less, or like not probabilistic or not monadic, but I'm going to use graphs. So a little more than sets. So the idea is, suppose we want to guide this robot, and we have these rooms here. So here are our rooms, and we want to guide the robot. Let's say the robot is here. And the goal is here. I don't know what that is. And the robot needs to get there, right? So the robot will plan out one thing. Maybe it says, I'll go here, and then I'll go here. But then at another layer, we can think about this. We have a finer grained system. And now we realize that the robot's not just in this room, it's in a particular place in this room. And the cake, or goal, not just in this room, it's somewhere here. Okay. And so the robot now needs to get from where they are down to there. So one thing we might want is we want to be able to say, okay, here's what I want you to do. Figure it out. And if you're the robot designer, you will have given a way to figure that out. So what you want is a way for this robot, and we can imagine that there are some obstacles, to actually figure out a particular path here. So there's a few features we might want. One thing we definitely want is that if we tell the robot to go get the cake, and it plans out a way to go get the cake, it's actually going to go get the cake. Another thing we might want is if we say, hey robot, don't go this other way, go this way. And then the robot figures out how to actually go that way, how to plan the intermediate steps, that it's going to actually be going that way. It's not going to pick a different path because at the point that it's decided to work its servos, a different algorithm kicked in, and it decided to completely chuck everything that was going on higher up. So we can constrain all these things using the notion of a hierarchical planner. So I learned this idea from David Spivak at this seminar. This definition I'm going to give is a little bit different from theirs, from David's and collaborators. And it's a little bit simpler, and it solves a little problem that they were having. And so I think it's rather nice. And it comes out of the general machinery of this open dynamical system stuff. So that was cool. Okay, so we're going to be in this setting here where this is going to be the coarse grain system, the coarse grain, or let's say high level, and this is the low level. And of course, this is just one step, but these things will compose, so you can do many, many levels. Okay, so we're going to model this as open dynamical systems. I'm going to simplify things by not doing the readout. In other words, I'm going to do the same trick I was doing over here. I'm going to take the readout to be the identity. So in that case, what this is going to be is, I need to tell you my setting for this. My setting for this is going to be graphs, and bundles are going to be maps into these graphs. And that's just going to be it. So it's going to be the slice self-indexing on graphs. So my S will be this graph here, the adjacency graph of this picture.
Sorry, maps.
Sorry, this will be S prime.
Maps in what category?
Maps will be, so maybe I'll set it up here. We'll have Bun from graphs to cap. And a graph here will go to all the graphs here with a graph homomorphism into this. So that's a map that sends nodes to nodes and sends edges to edges so that the source and target line up. And it's going to act by pullback on these things. Okay, so S prime, my high level thing, is going to be the adjacency here. S, my low level thing, is going to be the adjacency graph here. Now I have to tell you what my allowable moves are, right? So TG is going to be the bundle, which here is paths, points G in G, and a path out of G. And this is going to project down to G. So I'm going to regret calling this G later. Okay, so in other words, the fiber here, the allowable move, is a path out of my point. In other words, a move I can make is to take this path. Okay? So now I'm going to assume we have some set of instructions, and it's going to also maybe depend on S, but I won't be too particular about this. Yes?
What are the edges in
I'm going to take the set, just a discrete graph.
that? Oh, okay.
Yeah. And then I'm going to assume we have a set of instructions, and that set of instructions, I should mention, how does this act on if I have a graph homomorphism, it sends paths to paths, so this gives you the functoriality here. Now I'm going to assume I have a set of instructions, and these instructions maybe just tell me to go to this or that room. So we have S prime equals that, O equals S prime, and then I will also equal S prime, but it's going to be S prime sitting over S prime like this. In other words, I'm saying in any state you're in, I could tell you to go to any other room. And similarly here, we're going to have O equaling S, and I, this should be primes, and I is going to be S cross S into S. So in other words, what I'm going to get here is an update function, and this update is going to say this. It's going to take one of my, so I have S prime cross S prime to TS prime over S prime. So what I'm going to do is I'm going to take, I think I want to do this right. Ooh. I'm changing my example up on the fly. That's never a good idea. I'm going to take this function. It's going to send me a goal, and it's going to send me a path out of this, out of my starting point. I really want this to end at the goal, but this particular example doesn't do that. I'm already halfway through it. I'll be a little simpler here. I'm just going to use example 1 from before. This will save me some time later. I apologize. Don't change your examples on the fly. Not a good idea. Okay, so here, I'm still going to have this adjacency graph in mind, but this time what I'm going to do is I'm going to have my inputs here be my adjacency graph. Paths out of S sitting over S. And then here, S prime. And here similarly, this is going to be paths out S sitting over S. Okay, so my update here is going to say take a path, and I'm going to go to its endpoint. Be a little better. In other words, here's my path. I want you to walk to the end and get the cake. Here, we're going to have the same thing. We're going to take the endpoint. Says yes. S prime cross S prime. It's projection. So this is just saying that we're going to stay here. It's in its starting point. We go to an endpoint, and we'll get there. Okay. So now the idea is, how are we going to plan? What would it mean to give a planning system here? So there's two things we need. One is we need to know how the low-level states correspond to the high-level states. So planner. Me here, hierarchical. Well, planner. It's going to have a coarse grainer. G, and that's going to go from the high-level states to the low-level states. So that is the map here that's going to remove the lower grid. Right? It sends every square in here to the big room it's in. So if this is a particular position in your room, we're sending it to the room it's in. Next, we need a planner. And what a planner is going to do is a planner is going to take one of my paths here, my action plans, in the high level, and it's going to give me a low-level action plan. So that one is going to go like this. We're going to take our high-level action plan, and we're going to go to our low-level action plan. And this is going to have to happen in a way that's compatible here. So what that's going to mean is I have to take this here. I have to take G star I prime to I. So what this says is that a planner is going to take a high-level action, which is in the coarse graining of some low-level state, and it's going to give me a plan that's valid in that low-level state. So what does that mean? Here, I have this. Here's my path here in I. It would actually tell me to go from here to there. Right? I'm going to apply my function p, and I'm going to get this path here. And as we can see, it's the state I'm in here is in the starting state here. So that's what it means to be of this signature, G star I prime to I. Okay, and then there's going to be an axiom for what this satisfies. We need intuitively this to happen. If I have this high-level plan, and I'm in this state, because I'm actually at this point and in the room, and then I take my high-level plan, and I've given my low-level plan here. I execute my low-level plan, I move there. I should be in the room that my high-level plan said I was going to get to. And so what that looks like in terms of a square is this. We have G star I prime. So what we could do here is we can take this plan here and give myself an I. I can take that I and I can get the endpoint here. Or I could take the high level endpoint and give myself one here. And then here can coarse grain here. So this is G. Yeah. So, yeah. So is that idea clear? I kind of messed up my example there, but the idea again is that we have a high-level state, a high-level system, and a low-level system. And the planner is going to, and the high-level system takes in action plans and gives you new states. The low-level system does the same. And a hierarchical planner is going to involve a coarse grainer, which is a way of taking high-level states and giving you low-level states. And it's going to be a planner, which takes high-level action plans. Sorry, the coarse grainer takes a low-level state and gives you a high-level state. And the planner takes a high-level action plan and gives you a low-level action plan. And they have to satisfy this compatibility condition, which effectively says if you do the planned action, you'll get the planned result. So this comes into the other kind of morphism here, which I've... This is what I would call a contravariant morphism of open dynamical systems. So and this is going to be written with the contravariance on top. It's going to be a map on states, and then a lens on interfaces such that the sort of quote-unquote obvious square commutes. And this is also one of these mixed squares, so it's not entirely obvious what it means for this to commute. But there is a nice formulation that tells you. No.
Sure.
Yeah, this one's not either, because this is still not the right kind of morphism. But it's much closer. It's much closer. So,
Wait, so
yeah.
that's supposed to be, that's
Yeah, this is supposed to be vertical. Yeah, because it's...
But the one on the left is covariant, the one on the right is contravariant?
Yes, exactly. The one on the left is covariant, the one on the right is contravariant, and that's the trick, sort of. Now I'll just end my talk right here with that theorem. Theorem for any... The setup we have, there is a monoidal double category dyne of that open dynamical systems. Co and contramorphisms. So you get even weirder things. You can ask for cubes of these to commute, and commuting cubes of these form the commuting squares of this double category. I think I'll end my talk here, and then that can be my first question. Right.
Sorry, what's the...
Max, you go first. Oh yeah, just, is there an intuition for what the two cells in the double category are?
Yes. So what they mean in terms of the planning and the trajectories, it's tough because I don't know what what a planner means between like clocks. It's a reasonable formula that they would have to satisfy. I don't have specific examples of these squares working really well yet, except that I do have a nice double functor out of this thing.
Yeah, maybe one where the source of the trajectory, that part is just the identity, and then you have a planner for the other two. That seems like something reasonable.
Yeah, so what that would say is that the trajectories line up along the planners. Yeah, that's exactly what it would say, is that you have a high-level trajectory and then a low-level trajectory, and the trajectory that is happening in the low level was planned by the high-level one.
It implements
it. Exactly, and that is in fact the example of this double functor I have. I have this nice double functor that takes trajectories, and it gives it into a nice category of spans of behavior types. And so it tells you also that if you hierarchically plan, you get a nice, that variables are shared correctly amongst things. And if you also, should mention that contramorphisms also include the wiring diagrams. So not every contramorphism should be seen as a hierarchical planner either, just as not every comorphism is a trajectory. Yeah.
What's the
Good question. I did what I did last talk and not talk about it, but everything here is monoidal all the way through.
Starting with the bundle.
Starting with the bundles, a bundle is a monoidal index category, and you
it's
just
not, so this theorem isn't true for what you've written.
yeah, this theorem isn't true for what I think, but like it will be there. Like I'll parentheses there.
Can you give me just an example in one of your examples with a monoid?
Yes, it's almost always like a product, Cartesian product. So you imagine that two disjoint systems that are not interacting, their state space is the Cartesian product.
Okay.
And so the monoidal product here I call the sum of systems because they're sort of disjointly summed, even though it is implemented as the product of state spaces.
Okay.
Yeah. There's also other products. There's quite a rich structure on this double category. Yeah.
But because you included this in the theorem, it sounds like the monoidal structure is quite important.
Yes, it is quite important because you want to be able to wire these together. So you want to start with a disjoint sum of systems and then give a plan for wiring them together, and that's a map out of this sum. It's a contravariant morphism out of this sum. So it is important, and it's all there. It just would have slowed me down.
How do you model control loops here? So the hierarchical structure, you can't have cycles.
Interesting. Model control loop. So in other words, I get an error down there and I need to like force back up.
Yeah.
I'm not sure. That's a good question. Thank you. I'll look into that.
Is the vector field you had before another unit for this mode structure?
No, it's not like a tensor structure at all. It's really Cartesian product in that case.
You're not using tensor.
It's just in that example, it's Cartesian product. So the monoidal unit is the trivial system that is just a point that doesn't change. Yeah.
Alright, so let's do it again.
Thank you very much.